recording alongside. Ooh, well, Jade knows apparently. All right, so yeah, let me kick off the audio recording as well. Two. Give people 2 more minutes to join because we only got 30 some odd now. While we were giving people 2 more minutes, does anyone have questions about last class or anything else? Cameras are absolutely not required, by the way. I'm going to turn mine off in a second as soon as I share my desktop, which is where most of the material will be today because I am severely lacking in a whiteboard, unfortunately. Got a question about the GitHub. I just set up the account today, but I've got to actually move everything around. So clone the canvas up there and set up some scripts to switch between my multiple GitHub accounts now that I have multiple. And TA's got the notes. Excellent. All right, I guess let's kick it off. Let me share my screen here and we'll go from there. Let's just capture. Yep. All right, so this is the list of stuff we're going to cover today. I'm going to be hopping back and forth between terminals and tools and this notes section. Um, I do really lament the fact that I don't have a whiteboard. It was really nice to have a whiteboard that I could use while the code was up there to kind of circle stuff, which would be perfect for today. Um, the stuff that we're going to talk about today is not going to be in the notes that we've got. And the reason for that, I'm sorry, not the notes, the Intel manual that we have. And the reason for that is because all of this is not architecture specific. This is going to be compiler and operating system specific. But once again, once you know this, you can learn it on Windows, you can learn it on anything else. Nice thing is all this stuff is going to transfer almost directly to ARM or MIPS or anything else architecture wise. Um, the way that that kind of specificity breaks down is you've got stuff that's architecture specific, you've got stuff that's operating system specific, and then you have stuff that's kind of compiler and library and user space specific. And obviously there's like overlaps between those things. Like the way the architecture works kind of dictates a little bit how the operating system has to work at the low level. And the way that the compiler and the operating system work overlap because, you know, the kernel is built by the compiler, and the way that programs and libraries interact is going to be defined by the compiler and the libraries. The libraries are built by the compiler. But at each level there's different specificities and you can kind of mix and match between them. So today we're going to be mostly talking about operating system and compiler specific stuff. And what we're going to talk about is when you build a program, what actually gets built, and then how does it interact with the operating system to run as a program on the computer, and what are libraries and how do they interact with programs and all that fun stuff. Uh, However, the first thing I would like to do is kind of go over a couple more pieces that are architecture specific about assembly that we didn't go over last time. We were in that class directly to the 1 hour and 15-minute mark, which was perfect. but what we didn't talk about is branching and looping, which is kind of important for computer programs. So let's jump in there and quickly take a look at that. So let's see. I've got two example programs here. The first one is a simple branch program. So what I'm going to show you right now is how to figure out how something works, right? If you don't understand how branching or looping works and you want to know, what do you have to do to figure that out? Well, the move is you write it in a language you understand. That's native code. You compile that thing, and then you look at it and you see how it works. So that's what we're going to do here, and that's kind of what you will be expected to do as a hacker generally throughout your journey, right? You should at every moment be thinking, what do I not understand? Like what do I use on the computer and I don't understand how it's built. Well, let's build it and then go and take it apart and look at it, right? And that's how reverse engineering learning is going to work at the grad level. We're going to talk about that. Uh, if people want to stick around for another hour after this for a grad lecture, we'll start getting into more advanced reverse engineering. But here's a basic branch program. The only function calls that I'm using in here that you want to know about are A to I, ASCII to integer. Um, it basically just takes a string and returns you a number. Um, it's a signed number. It's not very specific. There are a lot of reasons not to use A to I, but it's very simple for this case, so I'm using it. The other one's printf. We've seen that before. So it's going to take an argument from the command line. If that argument uh, is a number that's greater than 256, it'll print greater, less than, it'll print less than. So let's give that a run and see how it looks. All right, so branch 50. Yeah, it's less than FF. How about 300? Yeah, that's more. Cool. Awesome, right? So what does that look like compiled? Uh, Quick other note about assembly here. What I'm showing you is Intel, uh, uh, what is called a disassembly flavor by GDB. So set disassembly flavor Intel shows you that. The other one that you can set here is AT&T. Uh, when Unix was being written, it was written at Bell Labs. And so they weren't using an Intel architecture. They were using a different architecture, and they have their own type of assembly visualization. Now, the opcodes and the instructions are exactly the same, but it's really obnoxious to read, especially for Intel. You want to use what the maker of the processor, you want to use their visualization of their assembly. So I've got a .gdb init file that just has this line in it. That's in my home directory. So when GDB starts up, this line is automatically run. If you open up your GDB at some point and you see a bunch of obnoxious percent signs, you just want to put that in a .gdb init and that'll deal with it for you. So let's go back and take a look. So we can break down this program real quick. If we were doing the same analysis we did last time, we would say main 0 plus 0 through main plus 3. That's our function preamble. We've got 4 bytes for a local. That's our number there. We can see that this chunk here is doing the work to pull something out of our argv, and it's argv1 again. Got that +4, so we say it's argv1. And we know from looking at the source that argv1 gets sent as the first argument for A to I, and then the output from A to I will be put in which register? I know you guys are muted, so EAX, right? Everything always comes out of EAX. So we see it's right here. This guy here is removing the argument from A to I off the stack, right? So probably our next chunk, if we were kind of breaking this up into chunks, would be here to here. That's the call to A to I, both grabbing the argument, calling, and then removing the argument. And the last thing on that line is EAX is being moved into an EBP -4 right? So we know minus is a local variable. That's EAX getting moved into that local variable that we defined in our C program. Okay. Now, the next thing here is compare, and that's the one that I kind of want to bring to your attention. So CMP, uh, let us pull it up over here. Now, I've done some cheating and looked at this beforehand, and I know that the first byte at that address is 81. So this is the line here. Compare IMM32, an immediate value with a register or memory. Okay. And so let's scroll down a little bit here and look at our description. Pairs a source operand with the second source operand, sets the status flags in the E flags register according to the results. Okay. What it is actually doing is just subtraction. Uh, Basically, this is a subtract instruction that does not store the result anywhere, but does set the resultant flags in the flag register. Um, you can read about the flags register. It's in the graduate reading, required reading, but everybody should take a look at the flags register. It stores a number of things about the last instruction that was run. Um, and some instructions set flags and some don't. So move, for example, does not set flags, but subtract and compare do set flags, add sets flags, and flags are things like, was the result 0? Was the result negative? Um, did the result overflow the register? So was the result larger than a 32-bit value? Uh, a bunch of things like that. And that flags register can then be read by other instructions. So this one here, jump less than or equal to. That's going to check the sign flag. It's going to check a couple others, and it's going to decide whether the value in EAX minus 100 uh, is greater than or equal to 0, right? And based on that, if it's true, it can only be true or false, it's going to jump to 50. And if it's not true, it's not going to do anything. It's just going to fall straight on through, right? So if I were drawing these as blocks, plus, let's say, plus 26 to plus 33, that would be kind of our conditional block. And then in the false case, we're going to have a call to puts, and that's pushing an immediate value. So that's something that we can take a look at in our debugger to kind of orient ourselves, x/a. Boom. We'll learn about how the debugger works. Specifically, I'll teach you in the lab that we're going to do next class. But for now, that's not what I wanted. I want /s. Yeah, there we go. So the string that's getting pushed here to puts is the one that we saw in our C, greater than FF. Small note here, our compiler decided it would be better off to switch printf to puts. It's a very similar function, except it doesn't take a variable number of arguments. The reason it did this switch is that we didn't provide format and variables to be put in the format. It's just a static string, so that's a safer and quicker function to run. So it swapped it out for us. So if we're blocking this out, the next block that we would kind of want to define would be right here. We push our argument, we call puts, we remove that argument from the stack, and then we're going to jump to the end, 63. If we go look at 63 right now, we can see that that's also pretty familiar, right? That's going to be our function end there. We're moving 0 into EAX. That's the return value for the function we call leave and ret. Cool. So let's suppose that our jump less than equal turns out to be true. So it's going to jump us to main plus 50, 91A8. Main plus 50, 91A8 is right here. And that guy is going to do something very similar, right? It's going to call push a static value, which we can determine pretty quickly. That's our other static string. It's going to call puts. It's going to remove it from the stack, and there's no need to have a jump here. It's just going to fall straight through, right? So that's kind of how these branches work is either you are going to go someplace else specific or you're just going to fall through to the next instruction, right? That's basically all we've got. Okay, so that's a basic branch. I'll show you the C again one more time. This is also on the canvas and it'll be in the GitHub. Uh, branch.c, right? So here's the local variable we used. Here's the call that gets replaced with puts with our static strings attached to them. We return 0, we're done. Okay, let's look at one other simple example here. We got loop.c. This is going to be a static loop. It's going to run for an iteration of hex 20 and just print it out in a while loop. So, oops, if I call it saga, it's just going to print the numbers, right? From X1F all the way down. So once again, function preamble looks exactly the same. There's only one local. It's an int. It's 4 bytes. We reference it here with EBP minus. You can see us moving the 20 in there. And then this one has a non-conditional jump. So a conditional jump would be something like JZ, jump if the value, if the 0 flag is set. JNZ, jump if the 0 flag isn't set. Jump less than equal, jump greater than equal. Those are both signed checks. Um, then there are others for unsigned, right? Um, but this is an unconditional. No matter what, we're going to jump to 31. And why are we going to do that? And we are going to do that because this is actually storing um, the conditional on our while loop. So we move the local variable into a register. In this case, you could use sub here, but the compiler has decided to use load effective address to just subtract 1 from EAX and store that in EDX, right? It could have used sub, but it didn't use load effective address. Then EDX itself is going to be EDX itself is going to be stored back in the local variable. EBP minus is local. And then we use another check, which is test. So let's go and look at what test is. Boop, boop, boop. Your instructions is passed out. It is going to be an MDU. Nope, not there. Um, yes, MTU instructions. Test, test, test. Test. Logical compare. Da, da, da. Computes a bitwise logical AND of the first operand and the second operand. Sets the 0 sign flag, the 0 flag, and the parity status flags according to the result. The result is then discarded. Okay. So test EAX is going to do what? It's going to decide if EAX is 0 or not, right? It's testing it against itself. If you AND something against itself, if there's a value in it, you're going to get a positive true value. And if there's no value in it, you're going to get a negative value. So we're just going to set the flags based on EAX, basically. That's all we're doing. Check test reg is just testing for 0. And then we've got JNE. So JNE and JNZ are the same. If you could read that as jump not equal or jump not 0. And it's the same exact instruction and different different disassemblers will show it to you differently. What it basically means is if I have subtracted something against something else, was the result 0? If the result is 0, the two things I subtracted from each other are going to be the same, right? Otherwise, it'll be negative, right? Or it'll be positive if it's greater or lesser. Okay, so if we're not 0, you go back to 15 and you run the actual loop or the code that's inside the loop. Now this time, uh, we've got two arguments here. The first is our number. Oh, I'm sorry. The second argument is the number, our local variable. And then this guy here is just going to be our static string. And because we actually have some operands here, not ASCII, but string, uh, that does not get changed to puts. It gets left as a printf. And here's the string from our C. This 0x is just to show that it's hex, and percent 08x is the format for show me it as a hex number, but also zero prepend it and make sure that it is shows me the full 8 bytes. So when we ran this, we saw that it just didn't say OX20. It said OX 00000020, right? 00000001F. And so that's because zero prepended, 8 bytes, hex. And then we remove that from the stack. So here's the actual work of the loop, and you can see that now we're at 31, and this is the checking portion of the while loop, right? That's what this becomes. And then the last part of this program here is just the function exit. Okay. So going back to look at it again, you can see this while count minus minus became quite a bit of assembly, right? While the printf was a very little bit, right? Push two arguments, count and this string, and call print. Whereas this guy had one conditional jump in it that made the loop go, right? And so we just decrement that local value and we jump until it's 0, right? So that's what a loop looks like in assembly. Has anybody heard the adage that you should never use goto in your C or C++? I'm going to assume the answer is yes, because we're not sitting in a class where I can see all of you raising your hand. Uh, the intrepid hacker knows that literally every branch in every program is a goto. That's the only thing the processor knows how to use is a goto, right? So when I say branch instruction, what I mean is any instruction that will change EIP to something that is not just falling through to the next instruction, if that makes sense, right? So those are a jump would be branch instruction, a call is a branch instruction, um, those sorts of things. All right, so that's us having covered our branching and looping instructions and a little bit on the flags register. I'd suggest you kind of read up on what those flags are, what they mean. Some of them are a little strange, like parity. Now let's talk about linking and loading and what binaries actually look like when you build them. So I'm going to be showing off IDA here. It's not necessary. I'll also show you how to do these things with some tools that you've got. You can do it with Ghidra, you can do it with Binary Ninja, you can do it with a free version of IDA. You can also do it with just basic Linux functions that you're going to have in your VM. So let's I'll pull up IDA. And which one did I put on here? This is the basic branch. So this is the one. When you pull up IDA, it's going to give you this graph thing. I don't like that, probably because I'm old, but also because I like to see as much data as possible um, when I am looking at a screen, not as little data as possible, which is why I ditch a lot of stuff. Let me see if I can make this bigger. No, of course I can't. I don't like that. Um, font. There we go. That's real big. Although we can't see the whole thing, so let's make it a little bit smaller. 20. That's better. Can everybody kind of read that? Yeah.
Yep.
Awesome. Thank you. Okay, so this is what we've got default here. We've got the functions as the disassembler has found them in the program. There's a number of them that come with main. And you can see the ones that are externals are pink, and we'll talk about what that means in just one second. But here's basically what we saw in GDB, right? And it's got some interesting things. Uh, this is a recursive disassembler, which is different than what GDB and objdump provide you, which are linear disassemblers. Okay, so what's the difference between those two things? A linear disassembler will be kind of greedy, and it'll just walk to the next byte, and it will assume that that next byte is the start of the next instruction, and it'll decode it, and it'll show it to you, and then it'll walk to the next one. Um, so if you had a program, for instance, where there was data in line and a jump over it, it would disassemble that data as though it were instructions. And then also possibly it would misalign the next actual instructions that occur. If you were to write some malware and you wanted to stump linear disassemblers, you could do that very easily in that manner. You would put a jump to the next valid instruction, and then you would put, oh, I don't know, the preceding opcode for a very large, maybe like an 8-byte instruction, and then you would let the next chunk be completely misaligned, and that would make it so that the disassembly was incorrect, right? A recursive disassembler pulls a bunch of nonsense tricks to actually interpret the code as blocks of code in the way that you should be thinking about it. So an example of this is I can kind of poke this jump target, and it'll actually show it to me here. You can use it to jump around like that or jump backwards. You'll see an XREF. So it stores a lot of information about the code, and it's doing some interpretation of the code, and it's using that to inform what it thinks is code and what it thinks is data. There are ways to upset these guys just as much as there are ways to upset linear disassemblers. Um, but in general, a recursive disassembler is going to give you a more accurate view of what a program does. And it doesn't necessarily need to understand where the start of a program is to do its disassembly properly. So if you're looking at firmware that isn't a standard format, right, then you're going to absolutely need a recursive disassembler. You won't need a recursive disassembler for this class, but just so you understand. The reason that I'm going to use it in this class, though, is because I want to look at the segments. Thank you. So when we compile a program, even a simple program like the branch program, let's see, and I have compiled this in such a way that it is as simple as possible, right? I'm not letting the compiler do any nonsense to this. That's why the make file looks so strange. I've turned off all of the optimizations and other stuff that goes along with it. But it's a very simple program. It references 3 libraries, and but you get a whole ton of stuff in the segment section. So let's take a look at some of that and the kind of data that we can get from it. Um, the first one to note, we talked about this, is the .text segment. This is small. Can I font it? I can. Make it 20. I'm going to scroll around to see stuff, but whatever. Okay, so the .text segment, you've got a start and end, and you can see it's an 0804, right? Everything that is loaded from our binary is going to be in an 0804 address, right? You can see it all here. And this is all in, you can put it in start order, right? You can see what the mapping is. So because this is code, you've got it's readable and it's executable. Everything that's executable must be readable because the processor has to be able to read the instruction before it can execute it, right? So if you see execute, you're going to see read. But what you don't see is W, unlike these guys over here, right? Um, so it's not writable, but it's readable and executable. That's where our code lives. We've got RO data, which is just readable and not executable. And this is going to store those strings, right? So all the strings in the program are going to be between A1000 and A17. They're .ro data, read-only data section. We've got some exception handler frame data. We've got some uh, initialization function pointers and some exit function pointers. These things are called at the start of the program and at the end of the program. We've got the global offset table, which is readable and writable, not executable. And the PLT, readable and writable, not executable. We'll get into exactly what those do in just 1 second. But you can see up here, we've got a PLT, which is code, readable and executable. Um, .data section is for data that has been defined by the program that is readable and writable. So if you have like an initialization vector for crypto that's going to be modified as the code runs, that'll be in the .data section, right? So that's different than read-only data. That's for data that should never be changed, static strings. But any global variables that you put in your program that have data to start with that may be changed later will be in data. And then you've got BSS, which is for globals that your program will need. It'll have to have space for it, but it doesn't have initial values for that data. So that tells it, okay, we're going to make space for this array, but because we didn't provide it starting data, it would be a waste to have all of that space taken up by the binary. So rather than actually having that space there, we're just going to have data about what space needs to be made when the program gets loaded, right? So anything in the data section, because we gave it initial values, all those values live in the binary. It's as large as it's going to be in memory. BSS is going to be expanded in memory when we load the thing up. Okay. Right. So we've got all these segments and all the values for them. Um, there's a bunch of other data on it, how those pages need to be aligned, and then these last guys over here are segment selectors. Right. So that's telling the program the loader. This is how I want the segment selectors to be able to address that memory. And here's the type of data that's going to be there, right? So the loader, the operating system itself needs to be able to look at this information, which lives in the header of the program. We can see it also here. Dump, let's figure out what it is. Let's see if I can remember. I want -X, I think. All headers, yeah. Dump -X. Show me all the headers for the program branch. Okay, so we can see a whole ton of stuff here. This is everything that's part of the ELF header for the program. Tells us what the architecture is. It tells us where start is in the thing. It's going to tell us, we're going to see all of the sections that we just looked at. All right here, right? So here's our text segment. Uh, the way that it shows us the code for this is that it's code, that means it's executable, and it's read-only, that means it's read and not write. I like the way that IDA and Ghidra and the other disassemblers show you this data, which is RWX in the same way that you would see it for a file. But that's what you're looking at right here, right? If we go to look at the BSS, we can see that it's data that's going, it doesn't have static data, but it needs to be allocated by the loader. So all this information is for the operating system to load this binary effectively into memory and then to start it, right? Um, so that's everything that's necessary to know is right here. Um, let's see. We talked briefly about that standard Linux address space, and you can see here everything in this binary is 0804. And when you look at the stack, it will be BFFF, and we'll look at that when we get into the lab at the next class. There's one other thing that I want to show you here, and that is the Where is it? Dynamic loading session. Let's do it like this. Capital call right branch. Yeah, there we go. Okay. So this is the dynamic relocation records. If we look at that same thing in IDA, we can see that here under imports. Okay. This is the program is going to expect to be able to run code that does not live in its binary, right? It lives in libc. And when we referenced libc in our code, we did so by including a header file, and then the header file kind of lets the program. You are going to have to be able to find this symbol in one of the libraries that you've loaded. Now, there's a difference between how Windows and Linux does that. So in Linux, what you are provided with when you compile a program that's going to load symbols from another library, you are provided a list of libraries to load in a particular order. And then what you're going to do at load time, you're going to walk down that list in order, and you're going to say, are you giving me a symbol called puts? Are you giving me a symbol called puts? Are you giving me a symbol called puts? Now, the way that this has been compiled, it's actually like the Windows method where it actually says puts at glibc 2.0. That means it's only going to look in glibc. This one, it's going to try to find anywhere, right? But these guys here, it's only going to look in glibc. And in a second, we will take a look at how that actually works. But what you need to see here is that both in IDA, in the imports, and over here in Objdump, you can take a look at uh, what needs to be loaded, and you can see an address for it. Okay. The jump slot is what Objdump calls it. But we'll look at exactly what that means in one second. Before we do that, though, let's look at one other thing, which is exports. Every binary is going to have exports. The things that are necessary to export are _start if you are a program that's going to be run by the operating system as like a base binary. If you are going to be a shared object, then you are going to export the functions that you want other programs to be able to call, right? So glibc is going to be exporting puts and A to I and libc start main and a whole bunch of other stuff. So when we first load this sucker up, we're not going to run main, we're going to run start. And start's going to do a bunch of things. And that's going to change based on what the operating system is and how it's been compiled, and a bunch of other things. But you will see one of the things that it does is going to call libc start main. That means it doesn't call main directly. It's going to move main into a register, right? And this is fast call, right? It's not pushing to the stack. It's going to send an argument to libc main in a register. So let's see if it tells us it's fast call. I believe it's telling me. Type extra function. Nope, it doesn't show me. Well, it knows. But it's going to do a bunch of nonsense before we start main. Some of that nonsense is going to be to initialize the heap. Even if our program doesn't use the heap, libc is probably going to use the heap. And the entirety of the heap is run by the library, is run by your main library. And in this case, that's libc, right? And it's going to initialize a bunch of other globals that it needs to run the programs it may be asked to run, right? It's going to be prepared for us to run any of its functions. But eventually, we're going to end up in main. and we're going to try to call A to I. Now, when we try to do that, that's the first function that we are going to call. And so let's take a look at where that actually sends us. Uh, where it actually sends us is to this .plt address. Now, what the PLT provides you is kind of a lazy loading. So the first time you call uh, A2I, you're not just calling directly in the library. You're going to call this stub that lives in the program that you yourself have compiled. And looking at it here is a little bit weird. Let's look at it in GDB the way that you're probably going to see it. Branch. Okay. Just as A2I. Okay, so there it's a little bit more direct. So it's going to jump to a an address. And so what we're looking at here with this DS colon is basically the same as if we're looking at it wrapped in brackets. It's going to go to that address, 0804 B1EC, and it's going to pull a pointer from that address and it's going to jump there. Now, this address is stored in the global offset table, the .got PLT. So let's take a look at that real quick. I'll say 2x 08 x 0804 B1EC. Boom. Okay, so got PLT. And that has got an address in it. And because we've never run this before, the address that lives there is the address at +6. It's 9056, right? And so what happens is the first time you run this, it calls this function pointer and it goes right back to itself. And then what it does is it pushes a number, and this is the ordinal number for A2I in libc. In Windows, sometimes you'll see this ordinal loading as well. So you can actually load by the number of the exported function inside the library call instead of by name. But in this case, what it's doing is it's pushing 10 as the argument, and then it's going to jump directly to the loader, the dynamic loader, and that's going to go walk those libraries and find the function pointer for A2I as it's loaded currently, and then it's going to replace this with the new pointer to the actual code, and then it's going to jump back. It's going to come right back here and run the whole thing again. And that time when it runs, instead of going to the loader, it'll go to the actual code. Okay. So if you never call A to I, it's never going to be resolved. This is a resolution process, right? So we are resolving A to I in this PLT code. Interesting thing to note here. The PLT code, it is readable and executable. It's not writable. Okay. The global offset table for the PLT is just an array of function pointers. It is readable and writable. Okay. This is a statically, relative to your binary, statically addressed array of function pointers that reference functions that the program will call. So any function, any dynamically loaded function that we care to call in a program has a writable function pointer at a known address in memory. Can anybody think of why that might be a fun thing to know? This time I'm going to wait for someone to unmute.
You can overwrite it with a function that would not necessarily be called by the binary originally, but might be to your advantage. And then the next time what the binary thinks it's calling the function that it's supposed to, it's actually calling the function you want it to.
Exactly. So was that Stefan?
That's me.
Remember when we talked about that unlink bug and you said, how do I run arbitrary code with it?
Yes.
Well, you had an arbitrary right. Here's a target, right? Right. So any dynamically loaded function, you can overwrite that pointer to, and you can point it at your arbitrary shellcode wherever it may be, as long as you know where it is. And you can also have your shellcode go back to the regular function and return that to the program so that after your shellcode is run, or perhaps after it's spawned another thread, that program will keep running just fine as long as you haven't messed anything else up except for these function pointers. Interesting point. There's a lot of stuff like this in here, right? So let's see if shoot, let's do this. What other stuff do I have that we've seen that might be fun and useful to overwrite in that same vein? Let's go to our segments.
So
We've got,
is the pointer not like protected in memory? So you can overwrite it like at any point with your own shellcode, pointing to your code?
yep, it is not protected because the resolution is greedy. That means lazy, sorry. That means that it at any point in time when you call a function for the first time, it's going to overwrite that function pointer, right? With that resolution. So the whole time the program's running, that's got to be writable and it's got to be readable.
So is that the reason that people that you said in the bit earlier that you shouldn't use a toy? Is that the main reason, or A2I? Is that the main reason?
No, no, every dynamically loaded function. Anytime you call a function that's in a library, which you will do constantly, that is the way it works.
Okay. All right.
Right. Um, there are some other interesting things here, like we have init and Fini, which used to be called ctours and detours. Uh, but but this calls some interesting code as well, right? So this guy here is an array of function pointers from our global offset table as well. So when we start the program, we're going to call something from that global offset table, and that's going to be initialization code in the same way that libc is going to call a bunch of stuff to kind of initialize the heap. Our program can do the same thing, and C++ has constructors and destructors, right? You're familiar with those on classes. This is the same thing for the program. So if we look at Finney, it's going to call something from the global offset table too. And that one has its very own, here it is, readable and writable. Here's the array. And so if there is a function pointer in here, which there is, do global detours, right? Destructor, auxiliary, array entry. You can overwrite that pointer as well and cause the program to exit. Even if there's no way for the program to exit, you can cause it to crash somehow. Before it exits, it will call your function pointer, right? So this is a great way to do this. Now, it used to be that you could make this kind of a but the stack. And if you grew the stack in a certain way, you could overwrite the destructor and kind of get control of things that a lot of people would say were not exploitable. That's no longer the case due to guard pages. I believe I mentioned guard pages briefly previously, but a guard page is a page mapped into memory without read, write, or execute, which means that if it's referenced at all, the program will fault. Arnab?
Yeah. So when we're like overriding like the point of memory address, this to clarify, is this only on when the function is first called, or is it when it's called each time?
Each time it's called. So let's go over it one more time. So
Okay.
here's the code that gets run every time you call A to I. It always calls the PLT. And the PLT will say, go to 0804B1EC, pull
Okay.
the function pointer there and call it. The first time you call it, that's pointing at the resolving code right here, right?
Right.
The second time you call it, it's pointing at the actual code. So it doesn't matter if it's been resolved before. Every time you call the function, this line gets called. And
Okay.
so at any point in time, you can overwrite this.
I see. All right. Thank you.
Yep. Yep.
You're overwriting the pointer in the GOT, not that pointer in the first instruction, right?
Correct. Yes. The instruction itself, this line here is not writable. This is code. It's got a static address in it, and that static address is the address to the writable global offset table, right? So here's what's writable is this memory here at 0804 B1EC. The memory at that address is writable. So this address here is the function pointer that points here to our loader, 9056, 9056, right? That's writable. And you can see the section is different, right? This is A2I at the PLT. This is AOI at the global offset table.plt. And that's, you can look at that in your segments here and see the difference, right? Here's our global offset table for the PLT, and then here's the PLT. Read, execute, no write. Here and here is read and write, no execute. Cool? How programs are run. Compilation, what's lost? We haven't talked about that. Okay, so in assembly, there is no idea of types. However, in understanding programs, types are the most important thing that you can understand. Now, how does this work? How it works is that uh, types are necessary for you to write C because they tell the compiler things about how to turn that code into assembly. But once the code is turned into assembly, the knowledge of those types is written in the assembly itself, right? The understanding the program needs for how to manipulate data is the assembly. The assembly is the information about it, right? So it's not necessary that explicit types be shown or stored in the program because the assembly itself is written to deal with those types. So you can figure out what the types are by reading the assembly and doing the reverse engineering, but it's not explicit. And that is why headers are attached to libraries. The headers provide the types and the argument types and the return value types for the program that the compiler needs to write the assembly properly. But once it's written the assembly, it no longer needs that data. That's why types are not stored in binaries unless they have the debug information, right? If you build something with the full debugging information, that will store the types and the debugging information. But a stripped binary will not store it. Like a Windows binary is not going to have its types in it. Now, standard Windows types, you can get the debug information for it, right? So if you're looking at NTDLL, everything that's in the Windows documentation that's public for you to write the code, you can pull those symbols from the Microsoft debugging server. WinDebug will do that for you automatically and show that to you. But if I were to write a program for Windows, or if I were to try to hack a video game or something, I would not see the types. My job as a reverse engineer would be to infer the types from the assembly. And that is something we'll talk about, say, in 20 minutes. Executables versus libraries. We talked about that. The difference is mainly just in the exports, right? That's basically it. Um, there are ways that you can use libraries, a couple ways that you can use libraries. The first is as a shared object or a DLL. That's going to be a dynamically linked and loaded library. And so you could call load library during the run of a program and load an arbitrary library and then try to resolve functions out of it by name, right? Or you can have that done. You could ask the compiler to say, hey, when I start, you are going to dynamically link this library and then you will lazily resolve the functions inside it. Another way to do it would be to statically compile. And what that means is that you would take a different format, a .a file, not a .so, in both Linux and Windows, and that becomes a part of the binary itself. That means that your program will still be able to call those functions. They will be a part of what is built as your binary. So if you were to just disassemble the binary, you would see all that code in there, and you would see static calls to specific addresses instead of to a PLT or other resolution function. Um, when you do that, generally the entirety of the library is brought along as well. And so all that code kind of lives in there. Um, so those are the two ways that you can link. And that static linking takes place at compilation time. So GCC line or an LD line would let you statically link that, and that would be in there for good. We talked import export, we talked headers, we talked PLT and GOT. Let's take a look at some other concepts in tooling in our last 10 minutes. So we looked at objdump. Objdump will show you a lot of stuff. You can use it as a linear disassembler. This should be in every Linux machine you ever come across. So if I do capital D, I'll use branch because that's what we've been looking at. That actually just kind of gives me all of the disassembly. Now, obnoxiously, it gives it to you in AT&T syntax. This is what AT&T syntax looks like. And it also will disassemble things that aren't code, right? So like it knows that this is a dynamic loading section, but it still disassembles it because I said disassemble everything, right? It knows that this is not code, but it disassembles it anyway, right? But also you get actual code. Let's find it. No, that's not it. That's not it. Main. There's main, right? So push EBP, move EBP, SP, et cetera, et cetera. It's all here, right? But it's not making any distinction between code and data. It's just linearly dumping it out. That's one thing you can do. We looked at using dash capital R. That just shows you the relocation data. Well, let's figure something out here. So what this shows us here is an offset into a table, but I am not certain whether it is showing us the PLT or the address of the function pointer. So let's go back in real quick and figure that out. Branch, yes, this as A to I. Boom. All right, so this is the address of the function pointer in the global offset table B1EC. And when we do this, it actually shows us the address in the global offset table B1EC. So the jump slot is the overwritable function pointer. So if I wanted to know what a good target would be, if I want to overwrite the function pointer to A to I, and I'm writing an exploit, I could just use objdump dash capital R, and it would tell me exactly what my write target should be. So say I have an arbitrary write. I can write whatever I want, wherever I want. It's also known as a write what where primitive. I get to write what I want, where I want to write it. What I want to write is the address of code I want to execute. Could be my shell code, could be another function, could be a piece of a function in the middle of a function, or a gadget was what we call that, right? Um, but this is the address we'd overwrite. That would be our target. That's our where. Okay, so very easy way to figure out where some of these guys are. Uh, and then the other thing we looked at for objdump is dash X is all the headers. So this is all the ELF headers. At the start of a Linux program, you can see with the file formats ELF32. It will break out all of the headers and show us what everything is in kind of an obnoxious way, a way that I don't like as compared to say IDA, but I'm an IDA person, so that's on me. You could probably just learn this and be perfectly happy. We can use LDD as another good tool. Will show us what libraries, what dynamic libraries this program is going to require to actually run properly. So we know that when we call this, one of the first things that's going to happen is that we're going to get libc.so6, which is going to have all of our standard library calls in it. We're going to get Linux Gate and LD Linux, which is probably going to do a translation for us for syscalls. Thinking actually based on people's desires, I will probably shuffle material around to do a single class on the kernel. How do people feel about that? Is that something you guys are interested in like the structure and how it works more deliberately? We'll get into a little bit of it with shellcode, but I think people have asked quite a bit. So we'll dig into that a little bit more, I think. LD preload. Let's talk LD preload. So LD preload is an environment variable. Uh, Environment variables are part of your shell. They get pulled into every program that gets run. Windows has environment variables too. If you right click on a binary and you hit properties, each binary is run with a set of default environment variables, and then you can add specific ones. On Linux, your shell, which is this thing we're typing in right now that lets us look at stuff, um, uh, that carries along with it a bunch of environment variables as well. So let's see if I can echo. I'll show it later. But it's a bunch of variables that and they're actually the third argument in main. You've got argc, argv, and then another one that looks exactly like argv that is envp. It's the environment pointer, and it's a pointer to an array of pointers to strings, and each environment variable is capitalized name equals the value it is. Um, and so that's one of the things that actually will shift your stack based on how many times you run a program or whether you're on a different system or if you're logged in as a different user or any of those things, which is why your stack is not always in the same place. That environment variable is changing constantly. It might store the history, so the last 5 commands you've run, which means you run another command, you just added to it, you've pushed the stack a little bit. Um, all those things are variable, but LD preload is an environment variable. And if you set LD preload, what it means is at the top of my list of loaded libraries, stick this set of libraries. Okay, so what you can do with that is you've got that lazy loading that says when I load this program, if it's not specified which library it's in, walk the list of libraries and find the first one that exports the symbol you're looking for, and that's the one you're going to resolve. Okay. And so if I had a program that uses a certain heap and I want to use a different heap, all I have to do is LD preload a different library that is going to be providing me malloc and free. And now when I call malloc and free, it'll go from the first one it found, which is the one I LD preloaded, not any of the subsequent ones, right? So you can kind of use that as a hook to replace function calls with your own versions. And you could use this, say, for fuzzing. You could use this to modify how a program runs, any program by taking over those functions with LD preload. Um, when we look at heaps, you're going to see a lot of that both in picking what heap the program uses, but also in kind of debugging heap failures. Um, we talked about guard pages. They can be used to do some really interesting things in terms of figuring out why a program is failing when otherwise it would be nearly impossible to do so, or it would take a lot of work to figure it out. And once we get into the heaps, we'll talk exactly about how to use those for debugging and understanding what's going on in a program. What else do we want to cover? What about
If you use
library?
LD preload to overwrite like a symbol to a function, does the like function you overwrite it with have to have the same take the same arguments as the original one?
Yes. Yep, absolutely. So what will happen is if it doesn't take the same arguments, so say it takes more arguments or fewer arguments, right? Your program that's calling it will still call it with the amount of arguments that it got from its header, right? The header determines that, and that's encoded in the assembly. That's never going to change. So if you take the wrong number of arguments or um, uh, especially if you're using ret_n, which will unroll those arguments from the stack, you will misalign the stack. When I say misalign, what I mean is ESP will either be lower than it ought to be, or it'll be higher than it ought to be when you return into the other function. And if it's higher than it ought to be, that means some of your local variables are going to be overwritten the next time you do a push or any other function gets called. Does that make sense? This is a
Yep.
tr
Is
yeah, this
libc loaded in all? Is that a standard for LD preload to have libc as part of that environmental variable?
I
Like, is it
believe
loaded
the
into every binary?
no, no, it's not. No, you can definitely build a binary that doesn't load libc. Absolutely can. Uh, the reason libc gets loaded is because I did pound include standard lib. That's why, right? stdlib and stdio uh, are calling libc functions, right? So, but you could statically compile a program that's very, very small that doesn't load any of that stuff. Even if it uses a heap, it's got its own heap in it, right? You can do that all manually. There's no need to have those things in there. Um, Let me finish the thought on the stack misalignment. Later on, we're going to talk about control flow guard, which forces you to only return into valid addresses. And one way that you can still beat control flow guard is to misalign the stack. So you will call a function that expects the wrong number of instructions, and that will create a different bug that you can then use to kick off what you actually want to get done, right? So a lot of the time in more advanced exploitation, we are going to turn one type of bug that may not be advantageous to us into yet another different type of bug that we can use more usefully in the situation. Arnab, am I pronouncing your name right?
Oh yeah, yeah.
Cool.
So for LD preload and like it can be used to like load in user implementations of functions, correct?
Correct.
So could you theoretically just load in your own version of a common function with the backdoor that you can exploit? Or
Yes, but if you can load your own library, you can already execute arbitrary code, right?
okay,
Once
yeah,
you've written a library and loaded it in, you're good to go. This is mostly going to be helpful for you to modify other people's programs to do what you want when you already have control over it,
okay, I see.
right? So,
So
sorry, go on.
yeah, so if you have a control, you can modify like a preloaded function with like something like a backdoor or something, and then that's loaded in to the system, correct?
Yeah, so one way that that would be useful is let's say you get access to somebody else's shell on a computer
Mhm.
and you set their environment to LD preload a backdoor, and every time they run the program, the backdoor gets run.
I see.
Right?
Okay. Yeah.
You could do that with a key logger, right? And
Yeah.
so that would be your persistence mechanism. Once you've already gotten control of somebody's shell, you want to get back in later. That's a persistence mechanism.
Right.
You could add an LD preload to their environment variable.
Yeah. And the keylogger is how you get back in. So that way, and then you can probably remove the backdoor after that, right? Because you already know the until they have changed their stuff, right?
Yep. Yeah, yeah. So you would do it temporarily until they do sudo and you steal their password and then you pull out their LD preload and
Yeah.
now you know their password and there's nothing to show them that you knew. So yeah.
So I'm just curious, how would you be able to access? Because you as root, can you just access LD preload regardless?
As root, can you access LD preload regardless?
Or do you have to like, because I'm wondering how you could potentially access LD preload because it's a variable, right? It's environment variable.
Yeah. So
So,
when you run a shell in your depending on your shell, it's going to load like an init file,
okay.
right? Like a .profile from bash. Generally, there's a bunch of environment variables set in there. So like my shell here, where it's my name at the machine colon my current path and they're different
Yeah,
colors, that's an environment variable, right? So every time the shell gets run, those things get initialized. And so if I wanted to, I can put something in my dot profile that did an LD preload, right? As root, you can always write to somebody else's files. So you could write to whatever their initialization file for their particular shell is.
yeah,
But those environment variables are set every time the shell starts. They're not set elsewise. Or you
right.
could set them manually. I could be like export LD preload equals blah, 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 blah. right?
Okay, I see. But that's only for that session. If like the system restarts, then it's set to the default, right? It's not saved.
Correct. Yeah. If I exit this shell and I start a new shell, it's not saved. Not
Got it.
not unless I wrote it in one of those config files.
Right. Got it. All right. Thank you.
Yep. All right. So okay. Let's take a break here and I'm gonna go grab myself some water. Everyone is dismissed except for grad students that want to stick around. And hopefully, Leon, who did our recording, can stop this recording now and maybe start a new recording.